Hello everyone, welcome back to Manasiya's classroom. Here I am back with another topic, time and space complexity. Now suppose I give you a simple problem, search a student record. One student writes a program, it takes 2 seconds for execution. Another student writes a different program, it takes 20 seconds. Now tell me which program is better? Obviously the one that takes less time. Similarly, if one program uses 10 MB memory and another uses 1 GB memory, which one is better? Probably the first one. So, whenever we design an algorithm, we need a way to measure its efficiency. And that is exactly what today's topic is about, time complexity and space complexity. When we analyze an algorithm, we are mainly interested in two resources. The first resource is time. How long does the algorithm take? The second resource is memory. How much memory does it consume? These two factors determine whether an algorithm is efficient or not. Algorithm analysis means determining the amount of resources such as time and memory required during the execution. Let's first discuss time complexity. Time complexity represents the running time of a program as a function of input size. Don't worry about the formal definition. Let's understand with an example. Suppose you are searching for a student record. If there are only 10 students, the search is quick. If there are 100 students, it takes more time. If there are 10,000 students, it takes even more time. As the input size increases, the running time changes. This relationship between input size and running time is called time complexity. So observe this carefully. Input size keeps changing, keeps increasing 10, 100, 1000, 10,000. The actual time may vary depending on the machine, but what we really care about is now the running time grows as input size increases. That growth rate is what time complexity measures. Now let's discuss space complexity. Space complexity tells us how much memory an algorithm requires during execution. Some algorithms require very little memory, others require additional arrays, temporary variables, or recursion stacks. As input size increases, memory requirements may also increase. So this is measured using space complexity. Space requirement consists of two parts. First part is fixed part. The second part is variable part. Let's understand both. The fixed part contains memory required for program instructions, constants, variables, arrays, and structures. This part generally remains fixed. Regardless of how many times the program executes, these memory requirements remain same. The variable part changes during execution. For example, memory allocation using malloc or memory used by recursive function calls. So this part varies from program to program. Now let's discuss different running time cases. Suppose we perform linear search. Array contains 10, 20, 30, 40, 50. We want to find 10. The element is already at the first position. Only one comparison is required. This is called best case. The algorithm performs under ideal conditions. Now suppose we search for 50. We must check 10, 20, 30, 40 and then finally we find 50. Every element must be examined. This is the worst case. The algorithm takes maximum possible time. Now suppose we search for 30. It is somewhere in the middle. Neither too easy nor too difficult. This is called average case. It represents the expected behavior of the algorithm. Another important concept is amortized analysis. Imagine inserting elements into a dynamic array. Most insertions are very fast. Occasionally, the array becomes full. Then resizing occurs. That operation is expensive. Instead of analyzing one insertion, we analyze a sequence of insertions. Then we calculate the average cost. So this is called amortized analysis. Now comes a very important interview question. Time-space trade-off. Suppose I want extremely fast searching. I may create additional indexes. Searching becomes faster, but memory consumption increases. On the other hand, if I avoid storing indexes, memory decreases, but searching becomes slower. Therefore, there is always a trade-off between time and space. Imagine a college of database. Option 1 stores additional lookup tables. Searching becomes very fast, but memory usage increases. Option 2 stores only essential information. Memory usage decreases, but searching takes more time. Which option is better? The answer depends on application requirements. సో మనకి ఎలా కావాలి, మనకి ఇంపార్టెంట్ మెమరీనా లేకపోతే టైం ఇంపార్టెంటా, ఎంత మెమరీ ఆక్యుపై చేసినా పర్వాలేదు, టైం చాలా ఇంపార్టెంట్ అంటే మనం మోర్ మెమరీని ప్రొవైడ్ చేయడానికి ట్రై చేస్తాం. లేదు టైం ఎంతైనా పర్వాలేదు, నాకు మెమరీ ఇంపార్టెంట్, కొంచెం మెమరీయే ఉంది నా దగ్గర అంటే అప్పుడు మనం మెమరీకి ఇంపార్టెన్స్ ఇస్తాం, టైం ఎంత పెట్టినా పర్వాలేదు. సో డెఫినెట్లీ దెర్ వుడ్ బి ట్రేడ్ ఆఫ్ బిట్వీన్ టైమ్ అండ్ స్పేస్. So let us summarize today's discussion. Time complexity measures running time. Space complexity measures memory requirements. Algorithm performance can be analyzed using best case, average case, worst case, and amortized case. We also learned the concept of time-space trade-off. In the next video, we will learn the most important topic of algorithm analysis, asymptotic notations, including big O, omega, theta, and other useful notations. Thank you for watching. See you in the next class. Do not forget to subscribe to Mana CS Classroom. Thank you.